Look up at the night sky, what do you see? We see a dazzling tapestry of stars. Each one represents a distant sun, many with planets of their own. Our home, Earth, is just a tiny speck in this vast cosmic ocean. Yet we've learned so much about the universe and its incredible journey through time. Join me as we embark on a journey through the cosmos.
Let's rewind the cosmic clock. Imagine a time about 13.8 billion years ago. There were no stars, galaxies, or even atoms. There was just a point of unimaginable density and heat. Then, bang! The universe exploded into existence in an event we call the Big Bang. It wasn't an explosion in the traditional sense, like a bomb going off. Instead, it was a rapid expansion of space itself. Imagine a tiny balloon suddenly inflating to an enormous size. But how do we know this really happened? Scientists have found compelling evidence. One piece of evidence is the cosmic microwave background radiation. It's a faint afterglow of the Big Bang, like a cosmic whisper from the early universe. The Big Bang theory is the best explanation we have for the origin of the universe.
In the first few minutes after the Big Bang, the universe was a hot, dense soup of elementary particles. Protons and neutrons, the building blocks of atoms, collided and interacted at incredible speeds. As the universe cooled, these particles began to combine. This process is called nucleosynthesis. The simplest element, hydrogen, formed first. Some hydrogen nuclei then fused together to form helium, the second most abundant element in the universe. Trace amounts of lithium and beryllium were also created. These light elements formed the raw materials for the stars and galaxies that would eventually populate the universe. The elements crucial for life as we know it, like carbon, oxygen, and iron, were forged much later. The atoms in our bodies were once forged in the hearts of distant stars. Stars are born in giant clouds of gas and dust called nebulae. These nebulae are scattered throughout galaxies and serve as stellar nurseries. Gravity plays a crucial role in star formation. Within a nebula, gravity causes clumps of gas and dust to collapse in on themselves. As a clump collapses, it heats up and spins faster, forming a protostar. The protostar continues to accrete material from the surrounding nebula. Eventually, the core of the protostar becomes hot and dense enough to ignite nuclear fusion. Hydrogen atoms fuse to form helium, releasing a tremendous amount of energy. The mass of a star determines its temperature, luminosity, and lifespan. From red dwarfs to blue giants, each star contributes to the beauty and complexity of the cosmos. Once a star ignites nuclear fusion in its core, it enters a long, stable period called the main sequence. During this phase, the star's outward pressure from nuclear fusion balances the inward pull of gravity. Our Sun is currently in its main sequence, about halfway through its estimated 10 billion year lifespan. But what happens when a star runs out of hydrogen fuel in its core? The star's fate depends on its mass. For stars like our Sun, the core will contract and heat up. This will cause the outer layers to expand, transforming the star into a red giant. Eventually, the red giant will shed its outer layers, forming a planetary nebula. The core will remain as a white dwarf, a dense, Earth-sized object that slowly cools over billions of years. For more massive stars, the end is much more dramatic. The core will either become a neutron star or, if massive enough, a black hole.
Stars are not randomly scattered throughout the universe. They are grouped together in vast collections called galaxies. Galaxies are islands of stars, gas, dust, and dark matter, bound together by gravity. There are billions of galaxies in the observable universe, each with its own unique size, shape, and history. Astronomers classify galaxies into three main types: spiral, elliptical, and irregular. Spiral galaxies, like our own Milky Way, have a distinctive spiral structure with arms winding out from a central bulge. Elliptical galaxies are smooth and oval-shaped, with little gas and dust and minimal star formation. Irregular galaxies have no defined shape or structure. They are often the result of galactic collisions or interactions. From the majestic spiral arms of Andromeda to the chaotic beauty of irregular galaxies, these cosmic islands showcase the incredible diversity and beauty of the universe.
Our home galaxy, the Milky Way, is a barred spiral galaxy. From our vantage point on Earth, we see the Milky Way as a band of light stretching across the night sky. This band is actually the combined light from billions of stars in the galaxy's disk. The Milky Way is estimated to contain hundreds of billions of stars, along with vast amounts of gas, dust, and dark matter. At the center of the Milky Way lies a supermassive black hole, a mysterious object with a gravitational pull billions of times stronger than our Sun. Our solar system is located about 2/3 of the way out from the galactic center in one of the Milky Way's spiral arms. We are constantly orbiting the galactic center, completing one rotation every 230 million years or so. The Milky Way is part of a small group of galaxies called the Local Group. Our closest major galactic neighbor is the Andromeda Galaxy, a spiral galaxy even larger than the Milky Way. In about 4 billion years, the Milky Way and Andromeda are predicted to collide.
Black holes are among the most fascinating and enigmatic objects in the universe. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. Black holes form when massive stars collapse at the end of their lives. As the core of the star collapses, its density and gravity increase without limit, creating a singularity, a point of infinite density. Surrounding the singularity is the event horizon, the boundary beyond which nothing can return. Anything that crosses the event horizon is trapped forever, pulled inexorably toward the singularity. Black holes are invisible to telescopes that detect light, but we can infer their presence by their gravitational effects on surrounding matter. Black holes challenge our understanding of physics and continue to be a subject of intense research and fascination.
When a star more massive than our Sun, but not massive enough to form a black hole, explodes as a supernova, it leaves behind a remnant core called a neutron star. Neutron stars are incredibly dense objects, packing more mass than the Sun into a sphere just a few miles across. A teaspoon of neutron star material would weigh billions of tons on Earth. Neutron stars are also incredibly hot, with surface temperatures of millions of degrees. As a neutron star spins, its magnetic field sweeps through space like a lighthouse beam. If this beam happens to point toward Earth, we detect it as pulses of radio waves, hence the name pulsar. Pulsars are incredibly precise cosmic clocks, with some rotating hundreds of times per second. Neutron stars and pulsars are fascinating objects that demonstrate the extreme conditions that can exist in the universe.
In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He observed that distant galaxies are moving away from us. Moreover, the farther away a galaxy is, the faster it is receding. This relationship between distance and velocity is known as Hubble's law. It implies that the universe is expanding. Think of baking a loaf of raisin bread. As the bread rises, the raisins move farther apart. Similarly, as the universe expands, the galaxies move farther apart. Astronomers use a phenomenon called redshift to measure the recession velocity of galaxies. The expanding universe is one of the most fundamental discoveries in astronomy.
While we have learned much about the universe, there are still many mysteries yet to be solved. One of the biggest mysteries is the nature of dark matter and dark energy. Dark matter is a hypothetical form of matter that does not interact with light or other electromagnetic radiation. We can infer its existence from its gravitational effects on visible matter, such as the rotation of galaxies and the gravitational lensing of light. Dark energy is a hypothetical form of energy that permeates all of space and is thought to be responsible for the accelerating expansion of the universe. Astronomers estimate that dark matter makes up about 85% of the total matter in the universe, and that dark energy accounts for about 70% of the total energy density. The matter and energy that we can see and interact with make up only a small fraction of the total content of the universe. The study of dark matter and dark energy is at the forefront of cosmological research.